Hi, welcome to this lecture on modular arithmetic, which is a part of our module on public key cryptography. So to talk about modular arithmetic, we need to first define the notion of congruence modulo an integer n. So assume that you have a and b, which are integers, and a positive n, then saying that n, so a is congruent to b modulo n, is the same as saying that n divides the difference between a and b. So the notation that we use is a is so a congruent to b mod n is this equality with 3 bars here. So that's the symbol to say that n divides the difference between a and b. Now, as an example, assume you have a equals 3, b equals 15, and n equals 6. So in that case, 15 minus 3 equals 12, and n equals 6 indeed divides the difference. So 12 equals 2 times 6. Now, which is one very important element that we're going to be dealing with is the notion of a congruence class. So these are going to be elements that we manipulate when we talk about modular arithmetic. But those elements aren't integers. Those elements are sets of integers. And in particular, they're infinite sets. So the congruent class of of a modulo n is all the x's in z that are congruent to the a mod n. So there are multiple notations for that. One that we're going to be using a lot in this lecture is a between brackets, but also a with a bar on top of it is pretty common. Now, in a lot of cases, we try not to overload this notation by not having the modulus appear. So when there is no ambiguity, that is not a problem. Now, sometimes when there are several moduli in the problem at hand, I'm going to have to introduce a little subscript that specifies the modulus. So for example, here we could use the subscript n, or perhaps like next to the bar to say to specify which modulus we're using. That will happen a little bit later in this video. Okay, so in particular, here, let's say the modulus is 6 and a is 3, then b equals 15 does belong in the congruence class of a modulo n, okay? Now, one thing that is really important to notice here is that, in fact, certain elements there are distinguished elements in those congruence classes. In particular, there is a unique one that belongs to the set 0 to n minus 1. So for each a and each modulo n, there is a unique x between 0 and n minus 1 that is congruent to a modulo n, which, as you remember, means that it belongs in the congruence class. So something we do a lot is we identify sometimes when we do modular arithmetic, we identify the congruence class with that specific distinguished number that belongs to it. Now, it's very important to know, though, that when we're doing it, we're simply, it's sort of we're being a little bit, it's a shortcut, so to speak, because in fact, the congruence class itself is not just that single element, but it's so convenient sometimes to just simply represent it by this particular distinguished representative. Now, the proof of that statement is the following. You assume that a is congruent to an x and a y that are both between 0 and n minus 1. Now we're going to try to prove that those two are in fact equal. So first we have that n divides both y minus a by definition of the congruence relation and also a minus x. Now adding those two relationships together, what you have is that n divides y minus x. Now we have assumed without loss of generality that y is the bigger number here. So what this means is we have two choices here. Either y equals to x, so this number y minus x is in fact 0, Or if it's not 0, the fact that a positive n divides it implies that n must be less than this number. But we had already assumed that because y and x were both between 0 and n minus 1, this latter possibility is just not satisfied. So we have to have that x is equal to y. And so x is congruent to a mod n. Now that x in question, this unique element, is easy to find. In fact, it's what we call a mod n. Now, what does that mean, a mod n, as opposed to a congruent to something mod n? So a mod n is the remainder of the division of a by n, so the integer division. So it has a remainder and a quotient. Now that remainder, which is between 0 and n minus 1, is denoted by a mod n. So this really important thing here to remember is that a congruent to b mod n is a relationship between two integers, but a mod n is an integer itself. The notations are very close, but not quite the same, okay? So not be very sort of stringent on that. And so a mod n is this particular element x, which is congruent to a modulo n, and that belongs to the set 0 to n minus 1. Now, we can do arithmetic between elements of, so between congruence classes. So we call the set, so we just demonstrated, because there's a one-to-one correspondence between congruence classes and elements of 0 to n minus 1, there are exactly n congruence classes. Now we denote z mod, so z slash nz, which was z modulo nz, the set of congruence classes modulo n. Now it turns out we can define arithmetic operations between those elements. Remember, those are sets. So whenever you decide to define a new arithmetic operation, especially on things that are not exactly numbers, it's good to remember to really be specific about what it means. So in the case of an addition, so between congruence classes, we'll say that the class of A added to the class of B is the class of A plus B. It's a very natural way, in fact, to define an addition between two congruence classes. And likewise, the multiplication between those congruence classes is defined as follows. We have the multiplication of the congruence of a class of A by the congruence class of B is just the congruence class of A times B, okay? Now, what's really important, of course, is that those notations be well defined. So it turns out that this is indeed the case, that if you replace here b by b prime, okay, but that is in the same congruence class, then in fact, the congruence class of a plus b prime is going to be the same as the congruence class of a plus b. Otherwise, this definition would just simply not have any sense. Now, as an example, what we have here is a equals 3, b equals 4, and for a modulus of n equals 7. So you have, so a plus b equals 7. And so the class of a plus b is the class of 0, okay, or the class of 7, that's the same. And now a times b equals 12. And the class of a times b equals the class of 5, because 5 plus 7 equals 12. So here what we have is an easy way to define an addition and a multiplication between congruence classes. And this gives rise to modular arithmetic. This is the arithmetic of congruence classes. Now, because we have defined multiplications, we can also talk about exponentiations. Okay, so naively, an exponentiation of a given congruence class by x is just the repetition of the multiplication of this number, of this congruence class by itself, x times. Now, if you do it naively, this will cost you x modular multiplications. But what if there was a better way? Now, assume that you can decompose x in in binary digits. So that what it means is you have a sequence of digits xi. So each xi is 0 or 1, and you have this identity here. Now, what you can do efficiently, and by efficiently what we mean is something that does not cost you as many operations as x. So here, that k is of the order of about log x. You can repeatedly square the congruence class of A in order to obtain A, so the congruence class of A, to the power 2 to the I for all the i's up to k, okay? And that will cost you only k multiplications, okay? Now, once you do that, you can notice that you have a to the x is a to the sum of all the terms in the binary decomposition, which you can break down. And then each of these terms here is going to be, so one of these elements that you have computed to the power the xi, which is 0 or 1. So basically, if xi equals 0, then the term simply does not occur in the product. And if xi equals 1, then we just multiply the term. And at most, you have k multiplications right there. So let's just work it out in an example. N equals 23, a equals 17, and x equals 17. So first, you need to decompose 17 in binary. So that's going to be 2 to the 4, which is 16, plus 1. And then you exponentiate. So you repeatedly square the congruence class of A. So you have a square, and then you square the square. That gives you a to the 4, and then you square that, and that gives you a to the 8, and then a to the 16. And then a to the 17 is just a to the 16's 16 times a. And you have performed here 1, 2, 3, 4, 5 multiplications, as opposed to the 17 that would have been required with a naive approach. Now, since there is a multiplication of elements that are in Z mod NZ, so congruence classes, we can also talk about units. So units, by definition, they're the classes of Z mod NZ that have an inverse, okay? So what does it mean to have an inverse? It means that there is another class such that when you multiply A by this class, what you get is the class of 1. And so in terms of the properties of the representatives of these classes, what that means is A is congruent to, A times B is congruent to 1 modulo N. Now, we have a notation. Remember, the congruence classes mod N, we denoted that by N mod NZ, and then N mod NZ star is the subset of that, that are all invertible modulo N. Now, it's not just a set, it's in fact a multiplicative group for those of you who are familiar with elementary algebra. And so what that means is units are stable by multiplication, right? You multiply 2 units and they're still going to be units. Now, as an example, so you have, for example, a equals 3, n equals 7. So if you do 3 times 5, for example, you have 15, which is 1 plus 2 times 14, which is congruent to 1 mod 7. So what we've shown here is that 3 and 5 are inverse of each other, or so that the class of 5 is the inverse of the class of 3 modulo n equals 7. So what we'll say is that a class has an inverse modulo n I mean, the class modulo n has an inverse, or that if you take a representative of this class, we'll say that this number, as a number, is invertible modulo n. We'll also say, by extension, that the representatives of this class are invertible and have an inverse modulo n. That inverse, of course, is not unique. Why the inverse of a class is a unique class, it contains infinitely many representatives. So if you consider a number, you cannot say it has cannot say it has a unique inverse. It has some inverses. If you grab, if for example, here what we have is 5 is an inverse of 3 modulo 7, but any number congruent to 5 mod 7 will also be an inverse of 3 modulo 7. Now, very important is Bezout's lemma. So we here state it in a simplified version, and I'll just explain in a minute what difference does it make. So here, if A and B are in Z in the coprime, we have that there exists U and V in Z such that UA plus BV equals 1, okay? Now, if they weren't coprime and in fact had if they had a non-trivial GCD D, we could have that UA plus BV equals D, okay? So, but here I just state it and prove it in a simplified way, because this is really what's important for us. Then we're going to use this lemma from Bezout to deal with inversions of congruence classes. But so first, let's talk about the proof here. So this is slightly more involved. You have to define first all the linear combinations of A and B, so all the numbers of the form XA plus YB for X and Y and Z. And with, so those linear combinations, to be in S, we require that they be strictly positive. So this is not all linear combinations, just the ones that are strictly positive. And then we consider the division of A by M, where M is the minimum of S. So here we define M to be the minimum, which it exists, okay? And we then take the division of A by M and call R its remainder, sorry. And so it's of this form, A minus Q times M, where Q is the quotient of that very same division. And then, because M is an S, you can replace it by XA plus YB, okay? And then you can shuffle the terms a little bit. So have the terms that are a factor of A on one side, and then the one that's a factor of B on the other side. And because you can rewrite R as a term that is a multiple of A plus a term that's a multiple of B, that forces it to be an S as well. But because R is the reduction of A mod M, we have to have that R is strictly less than M, and either R is an S, right, or R has to be 0, okay, because S is the set of those linear combinations that are strictly positive, okay? So we have a choice here, either R is 0 or R is an S, but since M is the minimum of S and R is strictly less than M, that is not possible for R to be to be both less than M and an S. So the only possibility that we're left with is R equals 0. And if that's the case, what that means is that M divides A. Now we can have the exact same argument to say that M divides B as well, just by reproducing the same calculation, except that starting with R equals B mod M. So what that means is we have the situation, M divides A and M divides B. So M is a common divisor of A and B. But we said that they were coprime. So the GCD of A and B is 1. So if the greatest So GCD means greatest common divisor. So M is a common divisor of A and B. The greatest common divisor of A and B is 1. So anything that is a common divisor of A and B has to be less or equal to 1. And so what we have here is, because it can be 0, then so what we have is M equals 1, and we have AX plus BY equals 1, and that proves the Bezout's lemma. So why do we care about that? Well, that's because we're going to be using this to find inverses modulo n. So first, we have a very important proposition. Remember the n, so the congruence classes z mod n, z are in one-to-one correspondence between elements between integers that are between 0 and n minus 1. Now, if we look at the subset of that that's formed of the elements that are invertible, then the correspondence is with the elements between 0 and n minus 1 that are coprime with n. So we prove that. So we first assume that a and n are coprime. Okay. So what does this mean? Because of Bezout's lemma, we have u and v such that ua plus vn equals 1. And so because of that, we can massage this equality and rewrite ua as 1 minus vn, which is congruent to 1 modulo n. So we have that u, the u from Bezout's lemma, is an inverse of a modulo n, or equivalently, the class of u modulo n is the inverse of the class of a modulo n. Okay, and we've proved here that the class of a is an invertible class, an invertible congruence class modulo n. Now, on the other direction, so far what we've proved is that if a is coprime with n, then it's invertible mod n. Okay, but to show that those elements between 0 and n minus 1, those classes where the representatives are congruent or coprime to n are exactly in one-to-one correspondence, we have to go in the other direction and assume now that the class of A is so the class of A is invertible mod n, and then see what's the consequence of that. So what it means straight from the definition is that there exists B in Z such that the multiplication of A and B is congruent to 1 mod n. And so A times B is of the form 1 plus k times n for k some integer. Now, we can rewrite this way, where A times B minus k times n equals 1. Now, what does this mean for a common divisor? So assume you have a common divisor of A and n. So you divide A and you divide n, and so you have to also divide A times B minus k times n. Okay, and if that happens, then you also, because it equals to 1, that means that you divide 1. And so the greatest common divisor has to be less or equal to 1, so it has to be 1. So now we've gone in both directions and we've exactly characterized the units mod n. Now next, we need a very important theorem, which is called the Chinese remainder theorem. So what it tells you is that there is a correspondence when n is equal to A times B, where A and B are coprime, then the classes modulo n are in correspondence with the Cartesian product of the classes modulo A and the classes modulo B. So here we go. First of all, what I promised you is that sometimes there is ambiguity, the classes, when you look at a number and you're wondering about its congruence, congruence class, and you have to specify sometimes which exact modulus we're talking about. Now, there are plenty of applications of the CRT. Here, we're going to be, in the next slide, specifically interested in having in evaluating the number of units mod n, depending on the factorization of n. So that's a very narrow applications we have in mind in this particular lecture, but the CRT is extremely ubiquitous in number theory. So as an example, let's assume, so you have 6 is equal to 2 times 3, they're co-prime, and so that means that the classes mod 6 are in fact in one-to-one correspondence with pairs of classes modulo 2 and 3 respectively. So what that means is if you're looking at, if you're wondering what are the x's such that x is congruent to 1 mod 2, so the class of x is equal to the class of 1 mod 2, and then the class of x is the class of 2 mod 3, well, this pair, I mean, there is a pair of classes modulo 2 and 3 that is in one that corresponds uniquely to a class mod 6. And so that's the class mod 6 in question is the class of that x that is both congruent to 1 mod 2 and to 2 mod 3. And in fact, there is one and only one, and in this case is x equals 5. Okay, so you have really this correspondence between the classes mod 6 and the pairs of classes mod 2 and 3, and it's given to you by for the class of x corresponds to the class of x. So the class of x mod 6 corresponds to the pair of the class of x mod 2 and the class of x mod 3, naturally. Now, how do we prove the Chinese remainder theorem? So we take the function that maps classes mod n to classes mod a and b by simply, and here I'm using as a notation subscript a and subscript b to specify that I'm taking the representative x and I'm looking at its class mod a and mod b. So what we're doing here is we take a class of x mod n and we map it to a pair of classes. So I mean the pair of classes of x mod a and x mod b. And then we want to prove that this function is one-to-one. So assume that f of x is equal to f of y. So what does this mean? So we have x is congruent to y in both mod a and mod b. So a divides x minus y and b divides x minus y as well. Now, there is a lemma that we're not going to prove here, but it's very elementary, that tells you that if a and b are coprime, then if a divides z and b divides z, then the product a times b also divides z. So here you have is a divides x minus 1, b divides x minus 1, and therefore a times b, which is n, will also divide x minus y. And what that means is x and y are congruent mod n, or equivalently, their classes mod n are, their congruence classes mod n are the same. And now f is injective, and we can directly conclude it's bijective because see the set here z mod a z is of cardinality, so it has a elements, cardinality a. This set has cardinality b, so it has b elements, and the Cartesian product of two finite sets has the number of elements as the product. Okay, so this thing on the left has cardinality a times b, which is n, and on the left hand side also has n elements. So if you have an injective function from two sets of same cardinality, then this is in fact a bijection. Now let's talk about the explicit CRT. So we assume that n is a product of coprime numbers, and we have that z mod n z is by induction from the CRT is going to be isomorphic to this product, this direct product. So what we have is assume that we're given this equation here. So assume that we're challenged to find an x given all the xi's. We're trying to find an x that is congruent to all the ai's, all the xi's modulo the ai's. So we first define the product of these ai's, and then for each I, we can define a divided by ai. Now, ai and the small ai are coprime because ai is made of the product of the small aij for j not equal to I, okay, and they all coprime. So it has an inverse that we can call yi, And then we form the following number here. So it's the sum of xi's, yi's, ai's. Now what happens is modulo, so for a given j, this is divisible by ai, and therefore, because it's divisible by ai, then it has to be congruent to 0 mod that ai. And then for when the I is the same, then modulo ai, these are equal to 1, and therefore we have, so this product equal to 1, and so this term here is congruent to xi, okay? So as an example, because this was a little bit sort of abstract to have so many terms, so let's go back to the simple case of 2 terms. And we're trying to establish what I had claimed before, which is 5 here is congruent to 1 and 2 modulo 2 and 3. So here we have that a equals 6, and then a1 equals 3, and a2 equals 2. Now the inverses are y1 equals 1 and y2 equals 2. And now I form my number, which is x1, y1, a1 plus x2, y2, a2, and that equals 11. Now, 11 is not between 0 and 5. And if you look at the one number between 0 and 5, that is congruent to 11 mod 6, that is 5. So we answered our previous problems. Now, we're going to use that directly in the calculation of what's called the Euler function. So the Euler function is the cardinality of the units mod n. So in an easy case, remember the units are in one-to-one correspondence between with the integers between 0 and n minus 1, which are co-prime to n. Now, when n is p a prime, then everything between 1 and so between 0 and p minus 1 is going to be co-prime with p, and so we're going to have that phi of p is going to be p minus 1. Now, if we have phi of p to the x, then we have, and for x not equal to 1, then we have to take out a few more multiples of p. In fact, we have to look between 0 and p to the x minus 1 and take down, exclude all the multiples of p. And so there are p to the x minus 1 such multiples, and so you have p to the x minus p to the x minus 1, which is p to the x minus 1 times p minus 1. And you see, so these are the numbers that are invertible mod p to the x, and that are between 0 and p to the x minus 1. Now, you see that it generalizes this case, right? Because you have p to the x minus 1. If x equals 1, then this term simply disappears, and then you fall back to p minus 1. Now, if a and b are co-prime and not necessarily powers of a prime, then what you have from the Chinese remainder theorem is that the units mod n are correspondence between units mod a and b. And so you have is phi of a times b equals phi of a times phi of b. So the strategy to find the Euler function, evaluate the Euler function on a number n that is arbitrary, is to first decompose, so first factor the number, and then use this previous lemma here that tells you that the evaluation of phi is in fact the product of the evaluation of phi on all the prime powers the different prime powers that divide n. And then you can use this one here on each individual term. So as an example, let's say you have 12. 12 is 3 times 4. And so phi of 3 is going to be 3 minus 1. And phi of 4, we're using this term here, is 2 to the 2 minus 1 times 2 minus 1. And that gives you that phi of 12 is 4. Thank you very much for your attention. And I'll see you soon for other videos on public key crypto.